Say you want to find the coefficient of x power 4 in this function. So when you will expand this, you will get some coefficient of x power 4. What will that be? One way to do it is using combinatorics. So if you know about generating functions, then this thing can be interpreted as distributing 4 chocolates between 6 boys. So each bracket, so you will write it like 6 times 1 plus x squared plus x cubed times 1 plus x squared plus x cubed, so on. So 6 of these brackets, and then each of them gives us some contribution. So it's like x power 0 or x power 1, x power 2, x power 4, and the exponents, they should add up to 4, right? So from each bracket, whatever term you get, the exponent of that, that's a contribution to 4. And that's basically saying that you want to distribute 4 indistinguishable objects into 6 distinguishable boxes or 6 distinguishable people or something like that, right? Because the number of ways of doing that, that is the number of x power 4 combinations that you can get, and that will appear in the expansion. So how would we do that? We can do that easily using the star bar theorem. Over here you just have 6 people, and that means you have 5 bars. So a bar is a separator. So over here the number of stars are just 4. If I put a bar over here, then that means that the first star, it goes to the first bracket. And then I put a bar over here, that means this star, that goes to this bracket. I put a bar over here, that means these two go to this guy. Sorry, the third one will be over here somewhere. And then maybe I put a bar over here, and since there's nothing in between in these two bars, that means nothing goes to the next bracket, and that means it gives x power 0 as its contribution, and so on. So you would have 6 such bars. So you would have 5 such bars, because 6 brackets, so you will need 5 divisions. 1 2 3 4 5 exactly. And you would need 4 stars, because x power 4, each exponent will be represented by a star over here. So number of ways to arrange these stars and bars, that will give us the number of combinations, and that is 4 plus 5 9 c 4, which is 126 if you calculate it. So that's good, but we missed something. The x power 4, that is not present over here, and we also consider that in this whole representation, because it also could happen that you just have this kind of a combination where the first bracket gets all 4 stars, but then it doesn't actually have x power 4 over here, so it cannot contribute 4 directly. So we need to get rid of all those combinations. And how many combinations will be like that? So you could give all 4 to the first bracket, or the second bracket, or the third bracket, and so on. And all the other brackets in every combination, those will receive 0. So the number of ways to do that, that is just 6c1, which is 6. So you subtract it from this thing, and that just leaves us with 120. So that's good. There's also another method of doing this. So you can write this thing as x power 4, or maybe let's say 1 minus x power 4 upon 1 minus x. So you could also write it as x power 4 minus 1 upon x minus 1, but I like to write it like this, that to the power of 6. Yes, like that. And then this is basically just 1 minus 6 x power 4 plus some other stuff, and that times 1 minus x to the power of negative 6. And we just want the coefficient of x power 4 stuff, right? So we can write this using the general binomial theorem as 1 plus 6x plus, so 6 into 5 upon 2, that would be 15. So plus 15 x squared, and then for x cube you would have, so sorry, it should not be 15, it's supposed to be 6 into 7 upon 2, well that is 21, right? And then you would need 6 into 7 into 8 upon 3 factorial, So that's just 3 into 2, and that would be 56. So plus 56 x cubed. So it's going to be alternate positive and negative for this negative x, but then it's also alternate positive negative for the negative 6. So it will be all positive. Cool. And then you also need an x power 4. So for that, 6 times 7 times 8 times 9 upon 4 factorial, that is 4 times 3 times 2. So this cancels with that, this becomes 2. It should be 14 into 9, which is 126, right? And some other stuff. Okay, just write it more clean. So this is going to be plus 126 x power 4 plus some other stuff, right? So all the higher powers, and this thing times that thing, if you multiply it out, or if you think about how it would be multiplying out, you would do 1 times all of that, then minus 6x power 4 times all of that, and so on. So when you do 1 times that, the only x power 4 term that you get is 126x power 4. When you do minus 6x power 4 times all that, the only x power 4 term you get is negative 6x power 4. So that's negative 6x power 4 times 1. And the higher powers, we won't consider them, because that multiplied with all of this will also only give higher power terms, and yeah, those are not what we want. And this combined just gives 120 x power 4, exactly what we got before. Now you might be thinking, why does this work? Like, this thing should give us a finite number of terms, but then this is an infinite series, and that times some finite number of terms, that should be an infinite number of terms. But no, the thing is that these infinite terms, well, they get cancelled when you multiply. Like, most of them get cancelled when you multiply this with that. So as an example, you can look at this. So 1 plus x squared, that's basically 1 minus x squared, that thing squared, and 1 minus x to the power of negative 2. So now this thing can be written as an infinite series, and then this thing that times this thing, you can write it like that. So you see that all these terms, they get cancelled out, and then you are just left with like the very higher power of terms. Those keep on getting cancelling out, and then if you think that the series would terminate somewhere, then that very high power term, that will be left, right? So for the purpose of approximation and stuff, we just ignore that higher power term. But then if you think about it in a very mathematical sense, like, should we include that very higher power term which would be at the end, then the answer would be no, because we know that this is pretty much the same thing as that. So there is no higher power term, and even if there was, like, its coefficient would be so low that for actual physical usage of this thing, you would just ignore that. So yes, it's just x squared plus 2x plus 1. Now there might be other proofs that we could do for this, like Taylor series and all that stuff, or just for getting x power 4, you could just write it as a Taylor series till the 4th term or 5th term and see what the x power 4 term is for yourself, right? But I think these two ways are sufficient, and these can be like used anywhere, right? I mean, they don't require that much of thinking or time. They also have a nice connection with combinatorics. And yeah, that's all I wanted to say. I'll see you guys in the next video.